going to the fault, as well as have enough sensitivity to operate a ground fault protective relay. And that's what an LRG does, or a low resistance grounding system does. Those systems generally limit the flow of current to the 50 amp or to 400 amp range, most commonly in the range of 100 to 150 amps. That allows enough current to flow to activate an overcurrent protective device or a specific type of ground fault relay, but also limits the amount of damage during the time of a fault. These are very, very common in industrial applications and have begun to be seen quite often into light commercial installations or heavy commercial installations. What also took off after that is, well, let's get the benefit of a solidly grounded system to stabilize our system voltage. That is one of the benefits of a solidly grounded system. You don't have the conditions of the transient over voltages as you did with the ungrounded systems. But the industry wanted to limit the fault current dramatically such that they can continue operating during a phased or ground fault. The classic example would be, as I said earlier, the pulp and paper mills. Specifically in pulp and paper mills or petrochemical plants, having those sensitive critical processes stop flowing can create some very violent situations. So what they need to do is during a time of a ground fault, they need to maintain the operation of their facilities such that they can schedule an outage, shut off valves, shut down processes, but maintain operation so they can schedule an outage very rapidly, I might add, in some cases. Hence, they began developing the HRG, or the high resistance ground. Now, the high resistance ground unit limits fault current to a maximum of 10 amps, usually in the 1 amp to 10 amp range, with 5 amps being generally the center point of the maximum, but rarely over 10 amps of current. However, there is no tripping. As we said earlier, what was happening with the solidly grounded systems is that you had a lot of current flow, but the breakers didn't operate because of high impedance in the return path. In this case, you're actually injecting a high resistive value in the return path to limit the available fault current that's flowing during a phased or ground fault to no more than 10 amps. There are very few circuit breakers, matter of fact, there's none on the market that will operate to protect a large power circuit with that low of sensitivity, not to be employed such to avoid nuisance tripping. However, in those applications, they have monitoring systems that are monitoring the system to tell the operator in a facility when they have a ground fault. And they have to use the same principles to go through and find this arcing ground fault condition.